So where's Vaughn? Is he still recovering from his drunken stupor after last night's game?
I'm sure. We're going to be live, so be aware.
Oh, yeah. Well, maybe I should add some details to that.
There you go, yeah. Okay, so we are up and going, so whenever you're ready to.
Okay, I guess I'm ready now. Welcome to our weather discussion for today. We had an aurora borealis last night that was very dramatic. And Pete's got some of the video here from our rooftop camera pointing northward, as you can tell.
Yeah, I was trying to get rid of that.
And tremendous amount of light pollution courtesy of the University of Wisconsin and the city, but it's really, it was early in the night. It was only like 10 o'clock, right? It went on for a couple of hours, people have told me. So there was ample time, in fact, if you were socially inclined, to alert your friends to the fact that something interesting was going on, knowing full well, if you're in this room, that clouds were likely to encroach tonight and into the evening. So the absence of such warnings leaves one a little bit discombobulated. No, I'm kidding. I'm trying to figure this out. I'm making fun of Libby. We saw each other coming in the building today. She goes, "Did you see the aurora last night?" And if I had known, I would have just, I didn't even know until then. I would have said, "Yeah, I wonder how come I didn't hear about it from anyone." So I guess this picture doesn't do it nearly the justice that you saw with your eye. You were up at Devil's Lake, you said, Libby? Oh, that must have been awesome. Much less light pollution up in Baraboo. I bet it was very dramatic and for it to last a couple of hours. So I wanted to make sure I could answer even the most basic questions about that for my class today, because there were a few. And I guess the most impressive aurora ever seen in the United States was in late August, early September of 1859. I just read that today. And people were able to communicate over telegraph without turning the switches off. There was so much electricity in the air from Boston to Portland. They were talking to each other on the telegraph without the switch being turned on. They did that on purpose. They said, "It seems like we're getting intermittent interference. Let's turn the switches off and see if we can still communicate." They had a 20-minute conversation with no switch on. Pretty wild. And that one, apparently, you could read the newspaper outside at night in that one. And there was even, in that particular event, the aurora was visible during the day. So it was really, really bright. I don't know what time of the day. It might have been close to sunrise or sunset. I don't know, but it was during the day. So anyway, beautiful, crystal clear night last night. I saw it when I came out of a dining event about 9 o'clock, maybe 8:30. The moon and Venus were brilliant. And if I'd only known, if I'd only stayed up, it would have been a perfect night to see it. Tonight won't be as good because we have an impending event. And we'll talk a little bit about that. So, I don't know, Pete, were you going to digitally remaster this, or you were talking about something? Maybe
This is just as a longer loop through the whole
Oh,
night.
okay.
So like right around 22 was probably the best, right in there.
So right in there, okay.
But then there was a couple more throughout the night, so I'm messing around with trying to get them. And then there's the northwest camera, but that's black and white. And I saw them on the corner of the east camera too. I'm going to take a look at that and see.
Yeah, so you can still see it floating around there.
We just got the east camera replaced, so it's back.
All right, great. So anyway, there'll probably be pictures floating around. We saw some in class today, people showing us. Either they took them or family members did. Really dramatic. And Ying Shun, I think, took pictures, right? And he's a really good photographer, so you want to make sure you see what he's got. Okay, here's our satellite for the last
today,
week.
or you want the week? Just today?
Yeah, I don't want to do the whole week.
Okay.
I haven't thought about it, so I don't have anything to say. Let's do the most recent. Yeah. So we've got a really interesting setup that we'll look at in a variety of different ways over the course of the discussion. Cloud mass that actually is part of this big cyclone off the East Coast, and the clouds are continuous pretty much from central New Jersey, Philadelphia area, all the way back to maybe Oklahoma City. And we'll see underneath all of this in the radar, this is an intermittent region of, fairly decent convective showers here and there. And it's a really strong horizontal temperature gradient, strong moisture gradient. So really the first very strong springtime frontal boundary and really nice springtime weather developing along it. What's beginning to happen, we'll see this better in the infrared. You can't see it so obviously in the visible because you can't always differentiate between the cloud heights in the visible. We'll be able to do that better in the infrared in a minute. You're going to see, I should say, the beginnings of the development of a cyclone here in far northeastern Oklahoma and Missouri, and it's going to be kind of riding up along this gradient and developing as it goes. And one of the consequences of that is there's going to be some really heavy snow somewhere in our vicinity tomorrow. And by vicinity, I mean within 150 nautical mile radius. I think it's going to be to our south and east. So it's going to be northern Chicago suburbs and far southeastern Wisconsin will get hammered, it looks like. We will get a little bit of snow again. After that inch, somewhat surprising, on, was it Thursday morning we had an inch of snow? And it just disappeared in the day, temperature went up to 50. It's a great thing about late March, you don't have to worry about it. But if you get 12 inches of snow, like they may in Rockford, you gotta worry about that for a couple of days. That's not gonna go away too fast. So we'll talk a little bit about that as the main forecast issue for this discussion. So we are now nearly a week from the, well, a few days, I guess, from the equinox. That was on Monday, right, the 20th? So we're almost a week from the equinox. And it hasn't really been a particularly warm month of March. It's been a strange winter. You know, we had a really sort of warm January and December, I think, and then February was about average, and then March, I don't know, I didn't look it up, but it's not been particularly warm. At least, I don't think so, but I haven't looked at the numbers. So let's take a look at the surface map.
Let's go pull this up for you.
So yeah, so here's the beginning of March is right about there. End of March is right about here. So yeah, I think most of the time we've been sort of in this range in the middle between the average high and the average low for our highs. So we've been cooler than normal on most of those days. There's been a few that have been above normal, but not many. And then a few really cold mornings, one time below 10 degrees, twice below 10 degrees in the month of March, right in the middle of it. So it's not been particularly warm. And contrast that with February, where we're kind of almost every day we're over the long-term daily average. Same was true in many of the days of January. We had the one cold outbreak right at the beginning of February. So yeah, not really a particularly nice month of March. Hopefully April will be nicer, but it's going to start out raining, looks like. I'll say that in the forecast as well. Let's take a look, Pete, at the infrared first, over the eastern U.S. So you can see there's a little bit more detail here. I think you begin to see something that looks a little bit more isotropic as opposed to linear on the southwest end of this long band of precipitation. And that's indicative of the beginnings of the development of a cloud head and a cyclone down there in southern Missouri, northern Arkansas. And we'll look at that from a couple of different perspectives as well. Okay, thanks, Paul. And can we now go to the, yeah, we'll take a look at the surface map and try and get a sense of what the temperatures are in the region of contrast, which is, again, from along a line like this is where all the precipitation is falling. So north of this point, you can see temperatures are all in the 40s. Some places are raining, but further north they're not. We're starting to get clouds here. It's still clear up to our north and west, but temperatures generally in the 40s. And then look at to the south, immediately to the south of this line. I haven't moved it, so no cheating. 61, 59, 73, 71, 70, and the dew points are all in the high 50s and low 60s. So this is a really substantial, look at the wind shift. A lot of winds from the south or southeast, and then here they're all from the east or northeast. So these are not only a pretty decent wind shift across here, but also a very decent temperature and moisture contrast. So the theta E contrast in the lower troposphere is really substantial across this boundary. With the vortex structure to it, that is a seedbed for potential development, so long as you can bring something along that can take advantage of the lower tropospheric vorticity. Because you know in the vorticity equation, convergence times whatever you have on hand for vorticity produces changes in the vorticity. So anytime you can get low-level convergence forced by upper-level divergence in a vorticity-rich region, you got a chance for development. So that's what we're looking at in this particular day. But look at some of these temperatures and dew points down south of Arkansas, or even southern Arkansas itself, 77 over 63. You've got 76 over 67 in the central part of Louisiana. New Orleans is 71 dew point, 79 temperature. Who wants to be there? Not me. Just miserable, okay? Too muggy for this early in the year. But that's fueling all of the precipitation that we just saw, or we will see here in a minute in the radar. Okay, so that's the main feature of interest across the eastern two-thirds, or say, of the United States. Let's take a look at, while we're doing it, let's take a look at the radar composite. And so here you can see exactly where one might expect, based on those observations and this short analysis that we've done of them so far. Precipitation in clumps, I guess I'd say. There's places where it looks a little bit less than continuous. Maybe that's elevation. I don't think so. I think there's just gaps in it. And then, because the same is true down here in southern Indiana. And so, but notice that it's speckled with some fairly high reflectivity returns. Southern Missouri, southeast Missouri, Cape Girardeau region, really getting hammered. This is not just individual thunderstorms. It's like a complex almost. And so that's where I think we're beginning to see maybe the beginnings of development at sea level along this vorticity-rich line. And so that'll be the interesting place to look and with implications for tonight and tomorrow morning in this region right here. Okay, one last thing before we go, we'll look at the West Coast satellite, but we might as well since we're here. Look at all this open cellular convection here over the Pacific Northwest. I happened to run into Carl Schultz, who's our departing provost. He's going to be president of the University of Oregon last night, out to eat. And I said, hey, sorry, we're losing you. You're a great guy, all that. Kind of things you're supposed to say to the higher-ups. And, no, I'm kidding, Carl. You are a great guy. And anyway, he takes out his phone. He says, yeah, my daughter goes to school at the University of Oregon. They got hail yesterday. I said, oh, that's routine whenever you get one of these cold air features aloft. So, well, in anticipation of seeing temperatures in the minus 35-ish range at 500 millibars. That'll be my guess today for all of this open cellular convection. And right there in Eugene, they're getting a pretty decent amount of hail, intermittent hail. And so that's not uncommon. Quilliam, Washington, the sounding station on the Olympic Peninsula, has more hail days than any station in the United States. But they're always this little pea-sized hail. It's not damaging, but they have a lot of them, and they're all post-frontal convective days, which is kind of cool. Okay,
Is there like a north-south ridge or something through there? See how the precip just disappears in that sort of linear?
Oh, right here?
Yeah.
That's probably just the Cascades. I don't know about southern Oregon, because then I don't know what the mountain situation is there, but this part here is maybe the Cascades.
I don't know if it's an artifact of where the radars are, or if it's actually drying and, you know, sinking on the
It
side.
could be a bit of both. I think the radars are not on the hill. One of them is at Seattle, the other one is down near Chehalis, I think, or someplace like that. And so I'm not sure exactly about that, and one is at Portland. But the Cascades is right there,
Yeah.
so that's definitely a factor, both for the radar shadow, but also, Pete, as you point out, some subsidence in the lead. So that's interesting. Okay, let's take a look at the 500 millibar map. No, West Coast satellite will be first. We're gonna do that. So here's what that collection of open cellular convective cells looks like in the infrared satellite. You can see it coming on shore. We saw that kind of widespread over the Washington, Oregon coast. A decent, but beginning to decay cyclone well to the northwest of his Hawaii. And so mostly the cloud head that's left is right there at the warm front northeast portion of the storm. Can't tell really from this angle what's going on at the dateline today, but earlier this week there were a couple of really impressive storms. Today, for the first day all week actually, the Pacific Basin looks a little bit more tame. It had been quite stormy on Monday and Wednesday, earlier visits in the satellite. And one last thing, pretty decent looking cyclone structure, maintaining that structure across the elevated terrain of interior Alaska. So that's the difficult task, I imagine. And this is a really oblique angle too. We have the Alaska satellite image, it would be probably even more interesting to see. So a lot of weather across the state of Alaska today. Okay, let's go to our 500 millibar super peak to begin with, Pete. So yeah, 12Z, look at that, 12Z Friday, the 24th of March, 2023. This does not look like the kind of 500 millibar map that gets me nervous about whether we get a foot of snow or 2 inches in less than a day. It doesn't really look like that to me, but that's what's in the forecast. So here are some of the elements. First, off the coast of Washington, look at that, minus 37 at Quilliam, so I was kind of on the right track. Minus 37 near Portland. So this is all minus 35 or colder right up there. And that, the reason I make that guess is because I've looked at this for 30 odd years or so. The spacing between the convective cells tells you something about the vigor of the updrafts. So the stronger the updrafts, the more widespread are the downdrafts. And so if they're spaced farther apart, it should be colder aloft because the stability then is lower, is my guess, and that's what provides the strong, environment for ascent. It's not really dynamically forced, it's all thermodynamically forced. So it's dependent on stability. So the farther apart those open cellular things are, the more intense are the updrafts, and that probably means it's much colder aloft. And so it works pretty well. If you pay attention, in the minus 35 range, that's about the spacing you get from those convective cells. Now, throw that problem at artificial intelligence, where you're actually measuring it, that would be a cool project, because I'll bet you it's straight up exactly the same thing, but you're not relying on my ridiculously faulty memory in that case. You're relying on some real numbers. But I bet you it's right. It would be a cool project if I knew anything about artificial intelligence. I barely knew anything about real intelligence. But here's the upper trough of interest. Remember, we had our precipitation band and vortex-rich structure all the way from Philly to about Tulsa. And the upper trough at 12Z is just upstream of that. So I think in the intervening several hours, this feature has migrated to the east. That's why we begin to see the maybe homogenization of the cloud and reflectivity over Missouri. It's no longer linear, it's kind of starting to look like a bit of a cloud head. That's what the approach of this upper trough is, my guess. We'll be able to show whether or not that's true in just a minute. There's broad confluence, as there has been nearly all winter long, at least the last several weeks, across the eastern and central part of the Great Lakes states. Coincident with a reasonable mid-tropospheric temperature gradient, that's probably providing the forcing for some of the ascent that's beginning to produce these cirrus clouds over us. But the main deal is coming further to the south and west. Okay, so let's go a little lower. Let's go to 700 millibars and see what we see with respect to some of these ingredients. So the trough at 700 millibars is just a little broader. I think it's a little more punchy, a little sharper at 500 millibars, and a little broader at 700. This analysis is terrible. There's not really any substantial orography there. That shouldn't look like that, but somehow it does. Same thing here. But if you kind of look past that and think about it a little bit more smooth, again, broad confluence over a temperature contrast, that certainly helps to provide the middle tropospheric forcing for ascent that's likely responsible, or involved, I should say, in the widespread convective activity that's across the Ohio River valley. So all those things are kind of connected in. And then the presence of a deep anticyclone over the eastern part of the Bahamas keeps this air that's coming in on the southern and western side of that boundary warm and moist. So that's a really nice setup for pretty decent precipitation in the Ohio River valley. You don't see any particularly obvious structures at 700 millibars, or I should say potent-looking structures over the Pacific Basin region. Just a little bit of a trough here, and there's some geostrophic cold convection and cyclonic shear, but it's weak. You don't often see that particular forcing really revving up at this level. A little higher you might see it. I asked Pete years ago to make the 400 millibar map. Almost no one does, because sometimes upper fronts really show up nicely at 400 millibars and only a little bit less nicely at 500. I really haven't paid enough attention to say how many times that's really paid off, but it has a few times. I know that. I'm glad you did it. Okay, so there's the front edge of our upper trough at 700 millibars is a little bit further to the east, as you might expect at this time, and that's kind of almost perfectly coincident with the southwest end of where that precipitation band is. So I think that's all connected. The development on the western end is tied to this upper trough. How about 850 feet? Let's see what the baroclinic structure looks like in the lower part of the troposphere. It's a little bit messed up here in the geopotential heights. There's no problem having it messed up over the mountains, but I'm confused about why it looks so ugly over the central U.S. What doesn't look ugly, though, is a pretty decent temperature contrast at 850. And that temperature contrast effectively ends at the warm edge of that rain band that we saw stretching across the eastern U.S. Everywhere south of there, it's uniformly about the same temperature, 15-ish degrees. Dew points are very high right near it, but they're very low coming in off the Gulf of Mexico. That won't probably last for very long. They'll be replenished by that flow. And the wind shift across this at 850 is not so obvious. You have a little bit of a light northerly, northeasterly wind here and something almost zero at Green Bay. So there tends to be a little bit of confluence located further to the east, actually, than over us at this particular time, 7 a.m. But decent baroclinic zone, and we're definitely cold enough in the Chicago suburbs and north of there, everywhere below zero, actually everywhere below about -4 or colder. That's pretty good chances if it stays that cold and it begins to precipitate, that it's going to fall to the ground as snow. Okay, so
That
that's
is a pretty terrible height analysis.
yeah, it's really bad. I haven't seen the 300 millbar map. Let's look at that, see if it does the same thing.
Look, that's the one line it does this. If somebody
Yeah.
turned in one like that and didn't have a good reason for why they drew it like that.
No, it looks like a gerrymandered map of the state of Wisconsin, you know, it's, we won't go into that. That might soon be corrected. Don't forget to vote a couple of Tuesdays from now. Let's look at the 300 millbar map. Yeah, suddenly the geopotential height analysis is nice and smooth. Looks really good. Very intense jet, though, and remember, I didn't bring much attention to it. The cyclone that was evident in the satellite picture is kind of offshore, well offshore, even the maritime provinces. That's tied to this jet, so right in the left exit region, where there's a little curvature as well, pretty decent cyclone sitting there. We saw that in the satellite. And then everywhere else to the south and west, right in this region, kind of at our longitude, we have the chance for some entrance region ascent, right about over central Illinois, northern Illinois. Maybe that's part of where the cirrus clouds are coming from for us. But the upper trough is down here near El Paso, and so again, downstream of that, throughout the whole upper troposphere, there's region of forcing for ascent over Kansas and Oklahoma, and that's where we begin to see some of this development. And I guess I will say this, to the extent that it's precipitating in the Ohio River Valley, that's going to tend to keep this ridginess downstream of the trough from flattening out. That's good for cyclogenesis. You want to have really sharp curvature in the flow, and if this ridge were kind of more suppressed, then you'd have curvature right at the trough axis, but then it would be straight flow the rest of the way, and that diminishes the amount of upper level ageostrophic divergence that occurs right to the east of the upper trough axis. So this precipitation that is well to our south is actually playing a role, perhaps, in setting us up for a situation tonight and into the early morning tomorrow in a subtle but persistent way. Because I especially see that here at 300 millibars. This is a fairly sharp trough at 300 millibars. One of the things about this trough is it's sharper with increasing height. And that's not always true, but it is in this case. And so we'll see what that portends for our situation. Okay, why don't we go to tropical, Pete? We can go through a couple of the maps, maybe draw a couple of cross sections. Then we'll go to Viz 5D and discuss some of the results that appear to be in the offing for us from the forecast. So let's start here. This is a 12Z run, and it's valid right about now. Look at that beautiful precipitation line. It's getting a little bit more intense in terms of accumulated amounts of precipitation across southern Missouri, Arkansas, into Oklahoma. Remember, that's immediately downstream of this upper trough, which is right around this region here in the Big Bend region of Texas. Downstream of that, that's where you have ascent going on right on the Oklahoma-Arkansas border, and that's where the cyclone's beginning to develop, 999 millibars. In fact, Pete, could we go to my Omega page as another place to bounce back and forth? Thanks. Sorry, I should have loaded that up. And 12Z might be in. I don't remember if it is or not. Let's see. Yeah, let's just try this. So this would be valid at 18. Is it in? Hey, it is. This is, no, it is, yeah, right?
18.
Yeah, this is it. Okay, this is it. Okay, so this is the 700 millibar vertical motion, quasi-geostrophic vertical motion from the same model run as we were just looking at. And so here's the ascent, and it is kind of maximized right on the Oklahoma-Arkansas border, and then the descent broadly back behind it. And this is only an approximation of the vertical motion, but it's one that you can actually diagnose. You can make physical sense out of what you see. So that's nice that it looks like that. Let's go back to the next time. Not this next time, but the other map, the tropical tidbits. So we'll have to bounce back and forth. Let's go ahead a couple, maybe 6 hours. Do they go at 6 hours on this page? I think they do. Yeah, 0Z Saturday. So one imagines that we will probably see the couplet of vertical motion with the ascent sort of over southeast Missouri and the descent down over parts of western Oklahoma. We'll check that in a minute. Let's go another time forward. And this is where it starts to get interesting. So this is midnight tonight. Cyclone was 999, I think it went to 998, 995. So a fairly weak development, but persistently getting strong, I would say that. And the precipitation is now getting much more localized around the new disturbance and kind of not really having this umbilical cord to the east. This is pretty heavy precipitation across a wide region. You know, it's probably half the area of the state of Illinois, even though it's only in southern Illinois. A little bit of snow creeps in over the southeast counties of the state and the northern counties of Illinois by midnight. Let's go one more time. I haven't seen this run yet. Oh, then it gets really interesting. 990, so that's 5 millibar increase in intensity in 6 hours. Nothing to write home about, but again, part of a persistent developmental process that's going on in this storm. This is a heavy snow band that stretches all the way from, I guess, Ludington all the way back down to Alton, Illinois. So that puts the northern suburbs of Chicago, Rockford, maybe Janesville, under the gun. This is at 6 a.m. tomorrow. One more time forward. And it's here quickly and gone quickly. By noontime, it's only snowing in Kenosha County, Racine County. It's gone from snow back to rain for us. How might that happen? Is it only snowing because the ascent is so strong and the precipitation rate is so intense, and then as soon as it weakens a little bit, it warms up fractionally to turn back to rain? If that's true, that's the kind of thing that happens in the month of March. So let's go to the precip moisture and 24-hour snowfall. We'll go to 10 to 1. Look at that. Look at that little bit right in there. Does it tell us the value on this? I can't
It gives
remember.
us a layout on.
But it's in the orange, so the green. It's at least, the darker green is like 18-ish inches of snow. So there may be some places in the southeast part of our state and just to the east of Rockford that are talking about a foot or more of snow tomorrow. And all of it in about 12 hours. I mean, it's gonna just come down suddenly and really snow. And Madison, we're on the border between 6 and maybe 2 or 3. Maybe we can go to another region. Maybe we might be able to see it a little bit more finely. Though I think there's only the north central US as an option, but it's a little better. 17 to the east of Rockford, what's that, DeKalb?
Yeah.
And then here it's gonna be more than that. So Racine, Kenosha, maybe get 20 inches of snow, unbelievable. And Madison is, oh boy, I'd say 3 to 4, maybe if you're in McFarland or somewhere in the southeast, you're in the 6 range. If you're up to the north and east, it's 1 or 2. That's currently the case. I don't want to spend the time, because you can do it on your own, of looking at several different forecasts valid at this time. But I think it's true that at least the last 3 or 4 have pretty much nailed this as the position of the main snow band. And that puts us just a little bit out of range. In the old days, you know, this is maybe a grid point and a half of the NAM model in the 1980s or early 90s. So if this whole thing is just a little bit further to the north and west for whatever reason, it's a whole different day than what it looks like now. And similarly in Rockford, we kind of avoid this deep snow, but it's going to be pretty wild tomorrow. So what I would like to do with the rest of the time is look at some of the forcing in some detail in association with this development. Let's do it first here, if we could. So let's go back to maybe lower dynamics. I think there's an 850 millibar frontogenesis. Yeah, let's take a look at that. So this is
Come down like when the roof failed in the Metrodome and all the snow came down in the field.
Yeah, right. And let's go back one time, Pete, because we were at the end of the snow event when we were at 12Z. I think it begins around 6, so maybe one more clip, right about there. So this is 850 millibar frontogenesis in the purple, and then the isotherms every 3 degrees are in red until you get to 0 or colder, then they're in blue. And so you can see right over the area that is the axis of the maximum snow band, fairly intense lower tropospheric frontogenesis, kind of centered right on Chicago, just about on Midway Airport. And so the tendency here is that and look at the winds, that's really what's going on here. The winds to the north are weaker and or parallel to the isotherms, and down to the south and east, they're a lot stronger, and straight from the south and east, it's strong warm advection into a region of little or no advection, so the differential of the temperature advection provides the frontogenetic activity. And so a thermally direct circulation responds to this, the depth of which is dependent on how deep that structure goes. We'll look at that in just a minute. And that will be responsible for dragging this lower tropospheric warm moist air upwards, condensing it out, depositing it into snow, and then dropping down to the ground. So let's take a cross section if we can, Pete, right through there. Perfect. And let's take a look at that variable, frontogenesis and omega. You have no control over the contour interval when you throw your hat in to tropical tidbits. And the problem with that is you can't really dial up what you want to show. So that's why I'll supplement this in just a minute. But the green lines are equivalent potential temperature. The shading represents vertical motions in pascals per second. So we're talking about purples are ascent and the grays are descent. So, and here in the purple solid lines are the frontogenesis contours. And from the ground to about 700, 650 millibars or so, you have a frontogenetic axis that is responsible for this plume of really intense vertical motion. My suspicion is that's what's dropping the snow. This is just more or less an open convection line to the south. So right about in the middle of this cross section, it's well down here. And you can see it has its feet sort of at 650 millibars. Look at how poorly stratified the air column is there. There's almost no vertical variation of theta E, whereas over here you're in the vicinity of a frontal environment where it's a lot more strongly stratified. Let's take a look at the PV while we're here, just because it would be interesting to see what it looks like in this developmental region. Not surprisingly, it's pockmarked at the top of these convective towers with all this ugly structure. And even some of the snow band, which I presume snow band is doing that. So this is not the kind of cross-section through an upper-level potential vorticity structure that really makes you think there's going to be a lot more surface development. This is a weak and poorly organized upper trough structure. And that's part of what we'll see in Vis 5D, as it turns out. So my initial hypothesis is that the snow that's going to fall will fall in allegiance to the position of this frontogenesis. In the forecast currently, that frontogenesis occupies the far southeast counties of our own state and the northern and northeastern counties of Illinois. If that were to change, I don't think the dynamics would change. I think the position of that particular forcing might change if the forecasts don't stay, looking like this. But that's going to be the engine that drives the heavy snow, I think. So let's take a look at Vis 5D now. And thanks for driving. We'll look at one time, and it's going to be between this time, 06Z, and the 12Z time. I set up the time at 9Z. Before we do any of this, let's take a look at sea level pressure over the map, just so we know where everything is. And I think it's already at 4 millibar increments. Okay, great. So our cyclone is about 996 or so millibars. I think the forecast at 995. So this is the GFS forecast. I think it's the same one that's portrayed there, smoothed a little bit. And so we've got all those ingredients the same. Let's take a look at theta E at the surface, just to get an idea. And I think we'll have to adjust the level. That's good. Half one is great. And let's do every, I think it's right there. Let's do every 5 degrees. I think it might be ugly otherwise. So there's theta E at about 400 meters above the ground. So this is the old baroclinic zone, the one that we're currently talking about, as draped across the country from, Philadelphia down to Tulsa. And it's along that we've kind of developed this cyclone for reasons that were described a little bit earlier. And so you can see this kind of a cold frontal theta E gradient that gets weaker over the western part of Tennessee and Mississippi, but it kind of picks up again along the coast. And then this is the warm frontal portion that connects back to the main cyclone out to the east. And right in there is the really intense lower tropospheric theta E gradient, lower even than what we saw at 850. So this is uniformly high theta E in this region. There's almost no contours across all of the southeast U.S. And as we saw, the dew points there right now are in the mid-60s, temperatures in the low 70s. That's the air that's being thrust into this frontogenetic engine. So there's a lot of water vapor available for conversion into liquid or snow. Okay, let's now take a look at, let's get rid of omega PZ and 2D frontogenesis. We'll do these one at a time. Let's take a look at theta in this cross-section going right through there. Tried to pick it at the region of strongest horizontal temperature contrast. So let's flip that up. And that's what potential temperature looks like. And perfect, thanks Pete. So here's the really strong lower tropospheric theta gradient that's associated with our feature. And then there's a mid-tropospheric theta gradient that's up in here. And they're not involved with the same isotropes. And that's always true, but this thing here is out ahead of the front edge of this. In fact, if we put potential vorticity on top, you can kind of see what the structure might look like. Here's the PV, every 1 PVU, so that's 1 and that's 2. And we've got right along this lower tropospheric temperature contrast, some pretty high values of PV. This is now several hours into the forecast, so that's a function of diabatic rearrangement of the PV in the column. And so it's been heated through the snow or rain that's been forming in here, and so you're generating PV right along the frontal zone where there's already a strong vortex contrast. And then here's the upper trough feature associated with this, and you can see that has a baroclinic zone with it as well, and that's the one that kind of finds itself maybe exactly at the same place on this cross-section as the one at the surface, but they're separate features. Okay? So let's now put the frontogenesis on here, which is, I think, the 2D, no, it's the other one, sorry, front 2DH. Yeah, this is just the rate of change of d theta dx, d theta dy. And look at that. That's where the frontogenesis is. We saw a little bit of this in tropical tidbits at 850, but it's even stronger higher up. And this is the whole engine, I think, is driving the ascent of this air. So let's now put omega on top of this. And where it's red is only ascent. So here's that plume of sort of convective activity out ahead. But look at how this plume of really intense vertical motion is perfectly married to this axis of frontogenesis. One expects there to be a thermodynamically direct circulation around this, and so all I'm showing is the updraft, but it's right there exactly married to that frontogenic axis. And there's theta. I think I might have prepared theta E too, Pete. Let's see if I have theta E. And let's make sure it's on the same cross-section. I just want to make sure of Yes, it is. Okay, now there's a little bit more detail here, which is really cool in the theta E. Now that's a little bit oblong. Let's get it rotated around the other way. There you go. Great. Okay. So let's take omega off for a minute, or W, it's W. And I'll take the PV off. We don't need that anymore. But what we're looking at now is theta E in purple and the frontogenesis, horizontal frontogenesis. So look at this theta E structure. We'll show it, I'll remind you again in a minute. This is the column that is the least well-stratified column in the whole region. Well, one exception. And that's where we have that big plume of vertical motion. This place here is a place where everywhere from here on down, theta E is decreasing with increasing height. So it's convectively unstable everywhere in this big lens. And that convective instability is being forced to rise by the circulation around this frontogenesis. So watch what the vertical motions look like. So it's really intense in the vicinity. Maybe this is a little bit off in terms of geographic relationship, but the strong vertical motion maybe has a convective component that's tied to this convective or neutral stratification. This thing here is the plume of extremely intense convective ascent as well. So, but this one here is tied to a strong forcing. And I think that something about the convective instability here, maybe it's only realizable right over in this portion, and it's not so realizable here because it's in between forcings perhaps. And that's why we get our maximum vertical motion right there at the lower end of this frontogenetic axis. And that would be at least consistent with the notion that you're getting pretty heavy snow falling back in here, and that's right about where Rockford is. So this whole thing is kind of, I think, driven by middle tropospheric frontogenesis, not really surface or very lower tropospheric frontogenesis. The surface is right about there where the pencil is. And so it's in the middle and upper troposphere, and that updraft is perhaps convective in the lower part because there's some convective instability to be had, and not so convective further up, but still pretty strong. So you've got a deep updraft that gives you the chance for some pretty heavy snow. So it's a pretty neat little case. And all of this is occurring quite separate, I think, from the developmental vertical motions that are fueling the cyclogenesis. So it's, I think I would put my money on frontogenesis and transverse vertical motions for this heavy snow event. So that's all I have. And
I was just going to say, like, it seems in the upper troposphere by the convective tower, the impact of what I assume would be the convective outflow on the isotropes that go towards the frontogenetical region.
yeah,
They widen the loft, which I would think help create like a stronger PV gradient horizontally, if that makes sense. So the wider isotropes right in that region, there's kind of a weird signature of vertical motion that looks discombobulated between the two.
yeah.
Isotropes are quite wide there. So I wonder if you just took away the convective system altogether, would you still have the same upper level forcing?
Well, I don't know. We can make a guess by looking at the PV. Let's take the theta E off, Pete, and we'll put the PV back on, but leaving omega on there. So, yeah, I think what you're saying is that this convective plume may be pushing this +1 PVU contour a little bit further up than it would otherwise.
Further towards
and that
the
increases this gradient. And a
Exactly.
consequence of a horizontal PV gradient in the tropopause is you have a jet maximum and so on. So that there's a whole bunch of feedbacks that might arise from this thing being there. It'd be really fun to try taking this out and taking out its historic presence in all of the feedbacks and see what happens. This might be the thing that allows for development of this cycle because you're creating this pretty strong PV gradient. The orientation of it relative to the thermal wind and all that is difficult to discern from one cross section. But one can get an idea. You could look at vorticity all by itself and see in the case with and without that thing, whether the vorticity in the upper troposphere is made weaker. Without it. I bet it is. I bet that's right. And yet this thing seems to be going on completely without regard for this.
Yeah.
Except for the fact that they're both feeding off of the warm, moist air. But that would be true for this even if this weren't happening. So it's very interesting how they seem to be kind of ships in the night a little bit here. But you're right, I think there may well be a diabatic feedback here, provided mostly by the liquid convective event that's further to the south and east, yeah. Yep. Any other comments or questions? Pete, thanks so much for driving. I impressed Pete to drive Viz 5D when I barely put it together myself, and he always makes it look so seamless, that's not easy, so thanks a lot, Pete. And thank you all for coming. We'll see you next week, which will be the 1st of April.